Hello, everyone. Thank you for joining today's CTSC Artificial Intelligence Seminar. We are delighted to welcome Dr. Jason Moore from Cedars-Sinai Medical Center in Los Angeles. Dr. Moore is a graduate of Florida State and the University of Michigan, and he's held a variety of faculty positions at Vanderbilt, Dartmouth, and the University of Pennsylvania, where he was director of the Institute for Biomedical Informatics. In 2021, he moved to Cedars-Sinai, where he became the chair of the Department of Computational Biomedicine. We are indebted to Dr. Moore for joining us today and presenting here on accessible AI for automating data science. Jason, thank you very much, and I'll turn things over to you.
Great. Thanks so much, Thomas, and thank you for the invitation and the introduction. And it's really wonderful to join all of you today. And I'll just start by saying, if there's a way we can collaborate, please feel free to reach out. My email address is at the bottom of the slide here. I'm a biomedical informatician and, importantly, a methodologist. I have spent my career developing artificial intelligence and machine learning methods for the analysis of high-dimensional biomedical data. I've done a lot of work in the genetic and genomic space, and more recently with electronic health record data. But I really love developing new methods. And as you'll see, the theme today is how can we make machine learning and AI easy so that everybody can benefit from it. I don't have anything to disclose. And let me start by saying that a lot of my work is really motivated by this concept of a learning health system. And that's certainly true now that I work in a hospital. And Cedars-Sinai aspires to be a learning health system. And this is a definition from an Institute of Medicine report from 2015, a system in which science, informatics, incentives, and culture are aligned for continuous improvement of the healthcare delivery experience. And the idea is that shown in this figure at the bottom of the slide is that we do a lot of research, the science, only some of that turns into evidence, only some of that evidence makes its way into patient care, and only some of that patient care improves the patient experience. And a lot of important information, knowledge, know-how, et cetera, is lost in this pipeline. And that's really the goal of a learning health system, is how can we tighten that up so that as much of our science as possible can find its way into improving the patient experience. And this is a figure I like that summarizes the process of a learning health system, starting with collecting data, as we do with electronic health records and research data. You have to assemble that data, make it accessible, importantly, analyze that data, which is what I'm going to talk about today. And then once you have good models, you need to be able to interpret that and deliver that as a message to the key people that make decisions. And then the hardest part of all, of course, is taking action to change clinical practice. Changing how clinicians practice medicine is a very difficult thing to do. But if we really believe in this concept of a learning health system, it's really critically important that each of these steps are interconnected, that they flow freely, and that this is a continual process to improve healthcare. So I'm going to share with you my vision for the future. I believe that if we really do aspire to be learning health systems, that access to data and all the steps leading up to the deployment of an AI model in the clinic, all of this needs to be seamless and easy. And as many of you know, it's right now quite difficult. It takes time to access clinical data from an electronic health record. It takes time to clean the data, to analyze the data, interpret it, convince somebody that it's useful, and then take the steps to deploy it in the clinic. All of this takes an enormous amount of time. And so this is a major motivating factor for my research program. How can we make this seamless and easy, just as shown in this kiosk here? Imagine walking up to a kiosk like this, entering an area of interest, a particular disease of interest, having the AI know what you're talking about, access the data, push a few more buttons, the data gets cleaned and prepared for analysis. You push a few more buttons, the analysis gets done. Push a few more buttons, the model gets evaluated, And then there's a pipeline in place for deploying that model in the clinic and doing the auditing, et cetera, to make sure that it continues to be useful. So this is my vision, and I'm going to talk about this middle part today, the easy data analytics, which I think we've accomplished. And I have an idea about how to do the other pieces as well. So let's start with machine learning. So you've collected some data, you've cleaned it, you wanted to develop a machine learning model to put into clinical practice. Machine learning is hard for a whole bunch of different reasons, but what's shown on this slide is the problem of choosing a machine learning algorithm. How do you know what the right machine learning algorithm is to choose? And what's shown on the left side of this slide, in each row is a different data set. Maybe the red dots are cases, the blue dots are controls. You have an X and a Y variable, let's say body mass index and low cholesterol. And what a machine learning algorithm is really doing is trying to build a mathematical function that separates the blue dots from the red dots. And you can see that going across for all these different machine learning methods in the columns, that each one is drawing a function through those dots in a different way. Some draw curves, some draw straight lines, some draw circles, some draw squares. And the numbers represent the predictive accuracy. So the higher the number, the better. And what this slide is really meant to illustrate is that each machine learning method looks at the data in a different way. And each data set has a different pattern to be detected, and that there's no one machine learning model that's ideal for every data set. And so this is one of the big challenges, is how do you know what the right machine learning method is to choose for a particular data set? This is a paper we published a few years ago where we looked at over 150 different data sets, did an exhaustive analysis across many different machine learning methods, many different hyperparameter settings. And you can see that for some of the data sets, like numbers 20 through 30, all the machine learning models perform similarly. So there must be an easy pattern in those data sets that every machine learning method can pick up on. But for some other data sets, like those between 70, 80, 90, some of the machine learning methods perform well and others perform quite poorly. And you can see as you scan across, there's a lot of heterogeneity here. And this just reinforces this idea that if you stick with one machine learning method, sometimes that might be okay, but other times it might not be okay. Now, if you want to do effective machine learning, you really need to build a pipeline. You need to piece together a number of different algorithms to really capture the patterns that are in the data set. And this highlights some of the decisions that you might need to make in putting together a machine learning pipeline. Starting on the left is feature selection. We often have thousands, or if you're doing genomics, you have potentially millions of different variables or features to choose from. And throwing all of that data in a machine learning algorithm is probably not a good idea. And so you might want to start with some feature selection. You might want to select a subset of variables that you think makes sense for your particular problem to make the problem a little more tractable. And there are a whole bunch of different feature selection algorithms that one could choose. And then you might want to do what's called feature engineering in that second step, where the data doesn't always come to us in the right representation. We might need to recode it or combine variables in certain ways. So this is what we call feature engineering. And of course, there are a whole bunch of different ways to do that. And then of course, as I've just mentioned, there are a bunch of different machine learning methods, and each machine learning method has multiple hyperparameter settings that need to be explored. And then even when you choose a machine learning algorithm, there are a bunch of different evaluation metrics that could be explored before you finally develop a model that you think is good. Now, once you have a model, the fun really begins, because you might want to determine, is the model understandable? Can you describe it to somebody? Is it usable? Can you put it into a decision support pipeline or into the electronic health record? Is it useful? Does the model actually do what you intended it to do? Is it actionable? And is it interpretable? Can you gain some new biological insight from it? All of this falls into what we call explainable AI, actually taking a model and turning it into something that's going to benefit patients. And there's a lot of work to be done in that space. So my goal is to democratize AI and machine learning so that absolutely everybody can benefit, so that you don't need to be a computer scientist or a statistician or a data scientist to do the machine learning. I firmly believe that if we're going to make progress as a learning health system, We need our clinicians, our epidemiologists, our nurses, everybody to have access to machine learning and to be able to ask and answer questions with it. And this is what's going to move us forward. Very much like when biostatistical methods like linear regression and ANOVA and t-test became accessible through user-friendly software. We need machine learning to be as accessible. Now, if I was to give a data set to everybody on this call and say, let's come back in a week, you can do any analysis you want with this data set, and we'll compare notes. Each of you would take a very different path through that data set based on your training, your experience, your expertise. Some of you might do parametric statistical analysis, but some of you might have certain machine learning preferences. Others might do more descriptive analysis. But I promise you, everybody would take a different path through that data set and try different things. And so I'm deeply interested in this question of how we as humans build analytic pipelines, how we make those decisions. And importantly, how do we get an AI? Can we get an AI to do that for us? To take the vast decision making out of our hands and automate this. And so that's been a major focus of my work going back to 2015. And that year, I hired a bright young computer scientist just finishing a PhD, Randy Olson, shown here. Finished a PhD at Michigan State University, and I was able to convince him. He was headed to industry, and I was able to convince him to come do a postdoc with me. And that summer, in the summer of 2015, we were brainstorming project ideas, and he came up with this idea of, well, what if we build an AI that can automatically generate machine learning pipelines? That would be pretty cool. And I agreed, and so we sketched out some ideas, and he spent 6 months coding and came up with the tree-based pipeline optimization tool, or TPOT, which, as I know now, is one of the very first automated machine learning algorithms developed in the world. There were a couple others that were developed around the same time, but we were among the first. And just to illustrate how early we were 2 years ahead of Google. Google didn't announce its first automated machine learning method until 2018. So we were well ahead of the curve, and you don't get to say you're years ahead of Google very often. So I like to brag about that, given how much popularity the big tech companies have. This is the first book on automated machine learning that came out in 2019, the very first book, and we have a chapter on TPOT in there. And what I wanted to tell you about today is a little bit newer automated machine learning software package and methodology that we've developed called Aliro. Now, TPOT was one of the first, but when we built Aliro, what we did was set out to build the easiest to use automated machine learning method. Again, this idea of democratizing AI, being able to put it in the hands of everybody. And the claim that I will make is that anybody can do machine learning with our tool. A 2-year-old can do machine learning with our tool. So that's the claim I'm going to make. So let me step you through the basic components of Aliro. And again, the goal here is to build an AI that can automatically generate machine learning pipelines, making all the decisions that I talked about earlier, to make it easy for anybody to do this. So the AI is doing the hard work, and you're just feeding it the data set and interpreting the results. So when we set out to build this tool, the first thing we needed was a machine learning code base. And the good news is that there's a very professionally developed, widely used machine learning library called scikit-learn. It's all in the Python programming language. It's all open source, so you can look and see the code behind all these methods. It does virtually anything you want to do in machine learning. So we were able to adopt that very easily. The next thing we needed was a controller. We needed a way for the computer, the AI, to pick a data set, pick a machine learning method, put it on a server, get the results back, and then do something with those results. And so this is kind of the automation part of this. And we started coding this ourselves, and I ran across this open source project on GitHub called Future Gadget Lab, which did exactly what I just described. So we adopted that. The next thing we needed was a database. If an AI is going to learn from experience and get better at building machine learning pipelines, it needs to have a memory. It needs to learn from experience. So we use a database to store all the machine learning results. So every machine learning result that the AI generates, every machine learning result that you generate as a user, all of that goes into a database, and that serves as the memory for the AI to learn from experience. And we use a type of database called a document store. And specifically, we use an open access database called MongoDB. And document stores are great because it makes it really easy to get data in and out, as opposed to, say, your typical relational database that you might build in Oracle or SQL, MySQL. And so here with a document store, what we do is every time a machine learning analysis is run, we code the analysis, the hyperparameters, the data that was used, all of the results get coded in a markup language called JSON, J-S-O-N. And you can just think of the results getting coded on a piece of paper. The piece of paper gets dropped into the document store, gets indexed. We can search for it and pull it out later. And this makes it easy to get lots of results in, lots of results out. And so this was the database that we built behind the scenes for the AI. So the next thing we needed was an AI, in other words, something that learns from experience and gets better with time. And the type of AI we decided to use is what's called a recommender system. And so when you go shopping on Amazon or any other e-commerce site, they will often suggest things that you might want to buy based on your shopping experience and the shopping experience of others. And this is an actual screenshot of my Amazon page about a month after I moved here to Los Angeles. And you can see it's recommending to me. It knows somehow that I've moved, and it's recommending cookware and Brita filters and office supplies and smart doorbells. And so it's recommending things to me that people who recently moved would buy. I'm not sure why it's recommending women's blue jeans, but maybe that had something to do with my wife's shopping patterns. But anyway, you get the idea that Amazon behind the scenes is using a recommender system. It's recommending to you the next thing that it thinks you're likely to buy to maximize sales. And that's very similar to how our recommender system works. What our AI is doing is looking at past experience and then recommending the next machine learning analysis to run on the data set, which it can do automatically. All right, the last thing we need is a way, again, if a 2-year-old is going to do machine learning, we need a way for the user to intuitively interact with the system. And so when you log into Aliro, this is what you see. This is the start screen. This is a web browser. Every square on the screen is a different data set. It shows the accuracy of the best machine learning result found thus far. For this first one, this appendicitis data set has about an 81% predictive accuracy. And there are 46 different machine learning models that have been generated for this data set. They're all in the database and can be explored. Now, all your data sets show up on the screen. And to do machine learning, all you have to do is push this AI button. So you load your data set as a CSV file, you push the AI button, the AI takes over and it does the machine learning for you automatically using its experience. And the more data it experiences, the better it gets. And I'll show you an example of that later. But this is how easy this tool is to use. And I think there's no reason why machine learning can't be this easy. There's no reason why you need a computer scientist to run machine learning. You might not understand what you're doing, but we make it possible for you to do it. Now, you can also do a manual analysis by pushing this blue button. That pulls up a preset menu of machine learning methods, commonly used machine learning methods. When you click on a method, it shows the parameter settings, the hyperparameters, and you just choose which ones you want and hit the blue button, and you're doing machine learning. There's no coding involved. It's that easy to do a manual machine learning analysis. And the neat thing of this, all of these results that you generate yourself also go in the database, and the AI can learn from what you're doing in addition to what it's doing. When the AI finishes, you get this screen here, which shows for a particular data set all the results. You can sort them by predictive accuracy. It shows you the algorithm. You can click up here on the algorithm and get all the details of the hyperparameter settings for each of the methods. And then this action button allows you to do two important things. First of all, you can download the model that was generated, and you can download the computer code, the Python code that generated this result using your data. So there's absolute full transparency of what the algorithm is doing. You can then take that Python code, you can study it, you can validate it on other data sets, and do whatever you want with it. So I think this is important because a lot of commercial AI software, sometimes they don't even show you the model, and they certainly don't show you what's going on under the hood, which which leads to a pretty significant lack of transparency. And I think for clinical applications, this level of transparency is really important. We need to be able to trust what an AI is doing, what it's showing us, what the model is, what the code is that generated it, so we can validate it. If you click on one of the results, you get a nice dashboard that shows the performance metrics, the ROC curve, we have some interpretation options in here, like permutation feature importance scores, which tell you what the most important variables are that are contributing to the result. We have things like Shapley values, if you know what that is for interpreting. We have that in here as well. So that's Aliro in a nutshell, and I've stepped you through the different components. And what I'd like to do next is show you a little bit of the evaluation that we did. But hopefully I've convinced you that we've developed a tool that's accessible to everybody and could fit into a kiosk like this, where you're just pushing a few buttons and moving your way through a data analysis for developing an AI model for clinical use. So maybe I'll stop there, and feel free to unmute if you have questions about the methodology itself, before I move on and show you some of the other things that we're doing with this tool and some of the evaluation. Does anybody have any questions at this point?
Yeah, can I just ask Andrew Vickers here, when you say accuracy, I presume you mean discrimination?
Yeah, usually you have like a case control data set, and so the accuracy is the accuracy of the classifier for predicting cases and controls.
Right, but accuracy is discrimination, or is I mean, accuracy is different from discrimination, but I think you're saying discrimination, AUC.
Well, AUC is a different measure than accuracy, but they're
okay. So you are talking about traditional accuracy, just so it's prevalent dependent, right? So I mean, if you have a 99% prevalence of something, an accuracy of 99% would be, you'd get that at random then.
It'll report balanced accuracy, so it adjusts for that that imbalance in the data set.
Okay. Because I mean, this just reminds me, statisticians have been criticizing the ML literature for years for ignoring calibration, right? Accuracy doesn't really matter. Discrimination doesn't really matter. Calibration is what matters, but you don't seem to be reporting calibration here at all.
Look, I think you're making an excellent point, and our tool reports all of the various metrics that you would want to see. So here we're reporting precision, we're reporting recall, we're reporting F1, we report the area under the precision recall score.
Well, I'm just saying, and this is on my mind because I just gave a talk at the European Congress of Radiology on this, and I showed these slides. There's 50 years, the first prediction models were built 50 years ago in Framingham. And since then, statisticians have come up with very, books have been written about this. It's all very well known how to evaluate, models. There was a series in the British Medical Journal just recently that said, how do you evaluate prediction models? And it was discrimination, calibration, and clinical utility. It wasn't F1 score, it wasn't recall, it wasn't prediction, it wasn't an ROC curve. So, I mean, you do have the AUC value there, I think, of 0.82. But you're only, it's just, it confuses me why we have a new technology and then we think like, oh, well, we don't have to learn the lessons that we've learned over the past 50 years with statistics.
So let me put it this way. This tool is open source.
Yeah.
So if you have a performance metric that you think is important that we have not included, you can add it to the tool. The other thing you can do,
but that's not my job.
we-
My job is, I'm like, just go read the literature and it'll tell you what it is. It's not my opinion. This is the consensus amongst the statisticians who do prediction modeling. Anyway, look, I don't want to take too much time. I'll let you get on.
Look, I understand exactly what you're saying. I'm a statistician myself, and that's why we make the tool open source. That's why we make the code that generates the model transparent. The Python code is there. You can take it and do whatever your heart's wishes are with the model. You can interrogate it. You can calculate a bazillion different metrics that are important to you that you think are better than whatever's provided in this tool. That's the beauty of open source and full transparency. With commercial products, you can't do that. You're at the mercy of whatever they provide for you. So what I would recommend, if you wanted to use this tool, is to collaborate with one of your wonderful bioinformaticians or data scientists at Cornell and modify the code to do exactly what you want it to do. But I appreciate your comments. I think it's important, and I'm with you. I'm not disagreeing with you. I think there are a lot of different metrics. I highlighted that in the pipeline slide that I showed earlier. There are a lot of different,
there are a lot of different metrics.
There
are a lot of different metrics, but you know, the statisticians who've done this for decades are on complete agreement of which ones are useful and which ones are not. And all I'm saying is, go and read the latest papers in the British Medical Journal on how to evaluate a prediction model. There's 3, and they tell you what to do. So like, start there, right? Anyway, I'll let you get on. I'm taking too much space.
Okay. No, I appreciate your comments and your question, and these are very serious issues. And I agree with you. I think if you want to put a machine learning model into clinical care, you need to trust it. And if that trust means that you've interrogated it in a way that the British Medical Journal feels comfortable with, then that's what you need to do. And our tool gives you full capability to do that.
These are great questions. Jason, before we move forward, there's a question in the chat. Dongmei Sun says, this is amazing. The data has to be in MongoDB, right? I believe so. I just want to confirm.
No, the data are loaded as a CSV file. So that's all you have to do is format your data as a CSV file. You can load it directly within the web app. MongoDB is only for storing the machine learning results. That's what the AI uses. So that's kind of behind the scenes.
Perfect. Thank you for clarifying.
Okay, so let me show you some evaluation. This is a paper we published a few years ago in bioinformatics. Bill LaCava, that was a postdoc at the time. He's now an assistant professor at Harvard and Boston Children's Hospital. And he's the one that developed the recommender system for this and did the evaluation work that I'm going to show. So when we first developed this, the big question we had was, is it actually learning? Does it actually get better over time and can get better with experience? And so what we did was we presented the tool with lots of data sets and random orders. That's what's shown on the x-axis. And then we did a comprehensive analysis of each of the data sets. So we knew approximately what the right answer was. And we looked at the change, the difference between the best result we knew the algorithm should find and what it was actually finding. That's what's shown on the y-axis. So smaller number is better, closer to the right answer. And we tried different algorithms for the recommender system. And you can see if you look at the blue circles at the top, that's if you just choose models randomly. You can see, of course, there's no learning happening, so that kind of serves as a baseline. If you look at the average performance of methods to choose the next best method, the yellow squares at the top, that doesn't really learn very well. But what worked best was a singular value decomposition on the data matrix, the results of the machine learning, all the machine learning results. And you can see that after about 50 data sets, there's a significant drop, a significant increase in performance. And as it experiences more and more data sets, it gets better with time. So these experiments convinced us that the algorithm was doing what it should be doing. It's learning with experience, getting better over And one of the common questions I would get was, well, okay, that's great, but how does this compare to other state-of-the-art automated machine learning algorithms that are out there? Autosclern was one of the first and also one of the most widely used, in addition to our teapot method that I mentioned earlier. So we actually did that experiment, Autosclern shown in red and Aliro shown in the blue circles, and we get almost, in some cases, as good and almost as good performance. Now, we didn't set out to develop the most powerful automated machine learning method. We set out to develop the most user-friendly, and we just happened to make also one of the most powerful. So it works quite well. And we wanted to do a real data example. And particularly, I've always been a skeptic of deep learning for the analysis of tabular data for classification tasks, especially with like electronic health record data. And so we wanted to find a paper where somebody had developed a deep learning algorithm on data that we had access to. And we found this paper that was published in 2019 in Scientific Reports, where they developed a type of deep learning algorithm called a long short-term memory algorithm, which is good for time series data. And they had looked at a data set that's available through a data use agreement called the MIMIC data set with 60,000 ICU patients. And there's time series data in there for oxygen and blood pressure, et cetera. And they had developed this fancy deep learning algorithm for predicting septic shock in this data set. So we applied Aliro to these data, and that's what's shown in the top half of the slide here. And these are the algorithms that Aliro chose automatically without our input. We also had a medical student in the lab at the time who was not an expert in machine learning, and we put them in front of Aliro and said, just run 5 machine learning analyses, whatever you want to. And so that's where the user is here in the table. This is the area of the ROC curve based on 5-fold cross-validation in the training data, and then this was a holdout data set that we then applied the best model to, which was a gradient boosting algorithm with these hyperparameters. Now, the important thing here, so the algorithm, Aliro did pretty well, and this is the long short-term memory here algorithm, had a testing accuracy of 0.86 as reported in the paper, and Aliro's model automatically identified had area under the ROC curve of 0.85 with overlapping 95% confidence interval, so there was no difference in the performance. And this is a baseline tuned logistic regression model here, which performs slightly worse. So the important thing here is that the long short-term memory, the deep learning algorithm took 30 hours to run on these data. Aliro was able to find a competitive model in less than an hour of time and completely automatically. And these are the important features that were found and the RC curve. So this, again, convinced us that Aliro could search through the machine learning model space and identify models that were competitive with human-tuned deep learning algorithms for this particular classification task. So Aliro is open source. It's available on GitHub. If you're interested in using it, we'd be happy to help you. And what I want to do in the last few minutes is give you an update of what we're working on now. And one of the things we've done is built a large language model tool into Aliro to add some additional functionality to the tool. And so what we've done is within Aliro, we now have an expert tab. And this is really for people who know what they're doing, who understand computer code. And so what you can do is, using ChatGPT, you can give it a prompt such as, I would like to remove outliers from this data set. Could you write some Python code to do that? That query through your login within our software goes out to ChatGPT. ChatGPT writes the Python code. We pull that Python code back to the server where Aliro was installed, to your server. It executes that code. The data set gets manipulated, and then you're off and running, and then you can do an automated machine learning analysis on that data set. So this opens the door to doing lots of interesting, novel things with your data without requiring a data scientist, or at least making a data scientist's job easier to write code and on the fly do interesting things with your data. You can do the data visualization. Kind of the sky's the limit. Whatever you can dream up to do with your data, as long as ChatGPT can write the code. Now we put this in an expert tab because obviously ChatGPT does hallucinate, and sometimes it writes code that is not accurate, and so you need somebody to review the code and make sure it's accurate before you trust the results. So that's why we put it in an expert tab, to let people know that you kind of need to know what you're doing to use this feature, but it opens a lot of doors. Then the next thing we're doing, and this is a big part of what my current research is focused on, is, one of the big problems with AI and machine learning is that it doesn't know a lot about the problem that you're studying. And so I have a grant on Alzheimer's disease to develop automated machine learning methods for predicting risk of Alzheimer's disease. And we've built what we call the Alzheimer Knowledge Base, or ALZ-KB, and have a paper in the Journal of Medical Internet Research that's about to appear on this. The resource ALZ-KB is at alzkb.ai. It's open access. But what we did here was we integrated more than 20 different sources of knowledge about genes, drugs, diseases, pathways, symptoms, etc., using a biomedical ontology. And we put all that into a special database called a graph database. That's what's shown here. We use a database called Neo4j, which is designed specifically for things that are in graphs. So here we have this graph database. The ontology allows us to model the semantic relationships. For example, this drug treats this disease, or this gene acts on this drug, etc. So we capture all those relationships. They're all in a graph. They're all in the database. Now, the downside of this is right now, this is how you query the databases through Neo4j's what's called a cipher query. So you have to know the syntax, and that makes this a little bit less accessible. So what we want to do is make this knowledge base easier for people to access so they can ask questions of it. And so what we've done is ask this question: can ChatGPT be used? Can a large language model be used to query the knowledge base so that you can ask natural language queries of it? So for example, you might say, show me all the genes that are connected to both Alzheimer's disease and this particular FDA-approved drug, and you want that gene list back. Can ChatGPT do that without me needing to write a complex query of the database to do that? The short answer is no. It had an accuracy of about 0.5, which is equal to flipping a coin. And it makes sense. ChatGPT doesn't understand this knowledge synthesis because that knowledge synthesis doesn't exist in all the documents that ChatGPT was trained on. So this was not a surprising result, but it raises the question, okay, how do we get a large language model to understand what's in our knowledge base? And so we use something that's been very effective with large language models called in-context learning. And briefly, what we have to do to get ChatGPT to understand our knowledge base is we have to take the knowledge base, put it in a special database called a vector database. And what you do is you feed the prompt and this vector information to ChatGPT. Now ChatGPT can understand, it's like we're speaking its language. It understands the knowledge that's there and the prompt, what we're asking, and it can generate a much better response. And so we tested this with over 1,000 true-false questions about the data, the knowledge base, and over 500 multiple choice questions. GPT-4, you can see, does not perform very well, has an accuracy of about 0.5 on these questions. But the in-context learning language model that we developed actually does much better. And we've added a new technology onto this, which I don't have the results to show you yet, but the performance of this has actually improved quite a bit. And we're about to submit a paper on this. The paper's written and will probably go out next week for peer review. Okay, so I'm excited about large language models because I think they're going to add a lot of utility on top of the automated machine learning that I've already described to you. I think expert knowledge is important to integrate with the automated machine learning, and ChatGPT for writing code opens a lot of doors to doing powerful things with your data just by saying a few words in a query. So this opens a lot of doors for using this as basically an AI data scientist to make your life easy. You have all this machine learning at your fingertips, you have all this knowledge about your disease at your fingertips, and you have all this code that ChatGPT can write at your fingertips. And I truly believe that this is going to revolutionize how we do data analytics and how we move forward as a learning health system. So I'll just end with a few thoughts. This is just an overview of our growing AI ecosystem here at Cedars-Sinai. It's really exciting to work in a hospital and have easy access to clinical data, easy access to clinicians. This is my piece of the puzzle here in the green, our department, Computational Biomedicine, and my new Center for Artificial Intelligence Research and Education, really pushing forward the research as I've just described to you. We have a wonderful health IT team, our enterprise information services, and they have a wonderful pipeline for evaluating, deploying, and monitoring, auditing machine learning models in the clinic. And we've already deployed, a dozen or so machine learning models in the clinic, with more in the pipeline. We have a division of AI in medicine in our Department of Medicine. We have a number of wonderful clinicians doing AI across our clinical departments. I serve on our AI Council, which exists at the highest level of our organization. We report directly to the CEO of our hospital to provide leadership and oversight for all the AI activities at our institution, and that's going really well. And we have a great accelerator program here at Cedars for working with startups and other businesses. And I'll just say as a side note that one of the great ways to gain trust with a commercial AI product is to be an investor and get the behind the scenes look, and to be a collaborator with a company. That's the only way you can really get an inside look at what's going on, understand the tool, look behind the curtains, and work with the company to make it better for your particular purposes. Otherwise, companies are just a black box and you have no idea what they're doing. And there's a lot of snake oil out there, I can tell you from my own personal experience, vetting AI companies that come here to our hospital. So I'll just end with a few thoughts about putting AI in the clinic and thinking about the impact of AI on patients and healthcare teams. And these are questions that I wrestle with every single day here at Cedars-Sinai. And there are many more than this, but these are just some of them. Will clinicians rely on AI too heavily to save time and money, thus exacerbating AI weaknesses? Will patients feel comfortable interacting with AI and knowing AI is being used for their care? Does the cost of commercial AI justify the benefits? And that speaks to some of the high costs that commercial companies will charge you. What is the recourse for patients harmed by AI? Who's at fault? Is the AI at fault? Is the clinician at fault? Is the AI company at fault, et cetera? Are there privacy and security issues unique to AI? Will healthcare workers lose jobs to AI? We just had the big writers and actor strikes here in LA last year, and that was one of their main issues and concerns was, will AI take my job? Is AI explainable? Do clinical users understand the AI, and do they trust it? What is the responsibility of the healthcare system for monitoring, auditing, and correcting AI? I think this is a lot of something that a lot of folks don't think about when they are pushing an AI model into the clinic is, the AI model might work well today, but 6 months from now, it might not because of data drift, the patient population changes, the instrumentation that's generating the data changes. Who's going to audit the AI and who's going to correct the AI if its performance decreases over some period of time? And what happens when we have 100 AI models that are deployed in the clinic? Do we have the resources to audit and correct all of those AIs? These are things we need to be thinking about. What is the carbon footprint of AI, and will AI in practice follow state and federal regulations and laws which are coming? Here in California, there are multiple pieces of legislation being considered that, for example, will require us to disclose to a patient when an AI is being used in their care. How will patients feel about that if they're told that an AI is being used in their healthcare? So these are a lot of issues to work through before AI can really be used for clinical benefit. So I hope I've convinced you that this is not science fiction, that we have the tools and the technology to make AI, developing AI tools, working with clinical data from our electronic health records, easy, accessible, and that this will play an important role in advancing learning health systems. So I just want to quickly thank the team. Nick Matsumoto is my lead software engineer, and Miguel Hernandez is my project manager that managed the Aliro project. And Jay and June have done a lot of the programming, and they're just a remarkable team and have developed all the large language model tools using really cutting edge methods. These are my grants. This is my Alzheimer grant that supports the ALZ-KB work that I talked about. My email, Aliro is open source on GitHub. ALZ-KB is also open source. And that's it. I'll stop there and take questions.
Jason, thank you. This was outstanding. You covered a lot of ground in a short amount of time. We've got about 5 or 10 minutes for questions, and I'll open it up to folks. Feel free to unmute or ask questions in the chat. And I'll go ahead and get things started. One question that comes up a lot these days is the need to democratize access to data to these methods. And I think the work that you've done here with Aliro is a massive step forward there. A big part of this democratization also involves the responsible use of these methods and of data. Team science is often suggested as an approach for doing this. A lot of the work that we're doing across the CTSA consortium, we find that the combination of roles, especially biostatistician, clinician, and informatician, is critical. As you look at tools like Aliro, where do you see the role of team science?
Yeah, well, I'm a big believer in team science, and I think for a tool like Aliro to be used effectively, it does require a team. We heard the comments earlier about the statistical point of view. I think that's important. In addition to clinical point of view, clinicians have to be intimately involved in the preparation of the data, making sure the right data is being used, making sure the data makes sense before using a tool like this, and then intimately involved in the interpretation, the selection of models. I mean, for example, a model can have a good area under the ROC curve or a good predictive accuracy, but if the model consists of somebody's gender, somebody's zip code, somebody's age, somebody's weight, and that's what's giving all the predictive power, those are things you can't change. You can't make people healthier based on their age by changing their age or their gender, et cetera. So that's a model that might perform well, but it might not be clinically actionable. And so clinicians need to be intimately involved in interpreting machine learning models and being able to explain them and trust them. So I'm a big believer in teams, and I don't in any way mean that a tool like this will replace a team, but what I would hope is that a tool like this would make a team faster and more effective at getting to an actionable model than going the old-fashioned traditional route of having programmers and data scientists, doing the work and the iterative process that takes.
Super helpful. Other folks who have questions?
Well, I mean, just following up from that, I mean, I'm glad to hear you say that, because you didn't say that during the talk. I mean, I wrote down a quote. You might not know what you're doing, but you can do it, was an actual quote during your talk. The first machine learning presentation I ever saw at a hospital, going on and on about the databases and the data flow. And they said that we found the biggest predictor of mortality was transfer between units, and therefore don't transfer your patients between units.
Right.
My partner who's an artist, like you laughed at it, my partner who's an artist laughed at it. but no one else around the room, because they were the AI and the data flows, and as a statistician, I as a statistical editor, I know how easy it is to do statistics because you can use the drop-down menus on SPSS, and I know the problems that this caused. And I know the problems that, if you make things easier, it doesn't get around all of these problems that, I think I don't think it's a good idea to allow people who don't know what they're doing to do it, because they'll come up with things that are harmful. And I think that that has got to be the focus. We now have a bunch of, we've converted a bunch of, we had muskets and now we have machine guns. And, we've got to be, we've got to be even more careful about gun safety, is my view. As a statistical editor, I spend most of my time editing papers done not by statisticians. There's no team science. It's some urologist or nephrologist goes on, puts data into SPSS and then writes a paper that has the statistics are wrong and the conclusions are invalid, and that's going to enter the literature. And our job is to try and prevent that happening. And if I was to give any feedback, is the comment that you just made about team science, I completely agree with, but that you should be made at the beginning, the middle, and the end of your presentation.
Oh, thank you. It's very, very good comments, and I do agree with you. I think there is real risk around misuse of machine learning. We see it all the time. And I'm an editor-in-chief of a journal, and I can't tell you how many papers I reject because they don't do basic things correctly. So I agree with you. But what I would say is that I think I think there are multiple values to a tool like this, but one of the values, and I think this was true for user-friendly stats packages as well, is that users of these tools are more likely to take the time to learn about machine learning. It's an entry into the field, and we want our clinicians to be educated about how to do machine learning, but also, as you mentioned, the pitfalls of machine learning. And the only way to really do that, to motivate them to learn, is to show them that they can put their hands on it. They can do it. Anybody can do a linear regression, and people who can do it and do linear regression are going to be more likely to learn the nuance of what makes a model a good model or what makes a model a bad model. And so I think there's a strong educational value to this. And if we aspire to be learning health systems, we need everybody to be well versed in the advantages and disadvantages of machine learning or any other analytical method for that matter. So I agree with you in principle, but I think I do think we need people everybody needs to be doing machine learning to learn about it. And that's the only way we're going to move forward. It just can't be me and you doing this for everybody. That's not going to move us forward very quickly.
Great questions, great dialogue. Looking in the chat, two related questions. And that's, have you considered how multimodal data types like images, audio, and so on could be incorporated into the Aliro architecture? And someone specifically asking about, what about images? And could this be used for, a bone and joint problem, for example?
Yeah, it's an excellent question. What I would say is that right now you can use Aliro for any problem that you can represent as a tabular data set that you can fit into a CSV file. So if you can convert your image data to tabular data, then yes, you can use Aliro. And with our other AutoML tool that I didn't have time to talk about, Teapot, that I briefly mentioned, we have published a paper showing how we can do text analysis and image analysis using that tool. So it's really about how you code the data, how you set up the problem. I get this question a lot because people would like to just be able to load images into Aliro and have Aliro process those images and analyze them. I would love for it to do that, but that would be a lot of work. But like I said earlier, the tool's open source. So if somebody wants to create a special version of Aliro for images, I would love to see that happen.
Perfect.
So it's
I
really
think
about data pre-processing.
no, that's great. And thank you for reminding everyone this is open source, and really appreciate your commitment to expanding the offering. I think we've got time for one last question. It looks like Larry has his hand up. Larry, I'll turn things over to you.
Thank you. I'm thinking about the unknown unknowns, touching on something you dealt with earlier. So if the year is, if the time is June of 2020, you have a database with all sorts of goodies about COVID, and you use these tools and you do something useful, but that was June. Comes July of 2020, Epsilon appears. How do you build into the system an awareness of the need to look for the unknown unknown? Epsilon didn't exist yet. We didn't know what to look for. But that manages the shelf life of the result.
Yeah, it's a good question. And as I said earlier, data does change over time, and people doing data analysis need to be aware of that, and that can greatly impact machine learning or statistical analysis results as data drifts, data changes. But I like your point about unknowns, and that's one of the reasons that we've developed this Alzheimer knowledge base, is to say, okay, here's what we know about Alzheimer's disease, and here's all the other things that have not been yet tied to Alzheimer's disease. And we're actively developing algorithms that can prioritize exploring the stuff we don't know about Alzheimer's disease to look for novel discoveries. And I think that's one of the great values of AI, and why we do machine learning and AI, is to say, what is unexpected? What, you know, it might be false, it might be a false positive, but AI and machine learning gives you a chance of finding the unknown, finding the unexpected in data. It could point to a bias, could be a real pattern, but I think that's why we do AI. We want to get at the unknown, we want to get at the unexpected, and we have to develop the knowledge bases, the tools that allow us to get at that, and also algorithms that are aware of the data and the changes in the data, which I think is what you're getting at in your question. These are all very important to doing a competent analysis.
You keep talking about the change in the data. I was actually focusing on the fact that reality itself is changing.
Yeah,
It didn't
absolutely.
exist, but the world changed.
Yeah, and that gets reflected in data. The data that we analyze, as the world changes around us, that gets reflected in the data.
Please join me in thanking Dr. Moore. We are beyond our time, and I want to respect Dr. Moore's time. Thank you all for joining us today. A special thank you to Dr. Moore for joining us from Los Angeles. We really appreciate the contributions that you've made here today. It was a great discussion, and I think there will be a lot of folks seeking to use Aliro and extend artificial intelligence into their research. Thanks again. Thanks to everyone for joining today. Take care.
Thank you very much. Take care. Bye-bye.